So when we first started taking derivatives, when we introduced it as the tangent line problem, we really were talking about a very specific thing about derivatives, where the derivative gives us the slope of the tangent line. Then once we got into it a little bit more deeply, we started looking at the derivative as a function. So we could plug in any x value, and when we plug that x value into the derivative, we would get the slope of the tangent line at that point. So when we take the derivative of a function, we get another function. Well, since we get another function, what can we do with that function? Take the derivative again. So what we're going to be doing is taking derivatives repeatedly, taking the derivative of a function over and over again. So if we have something like y equals, say, x squared, we can take the derivative, which would be dy dx. So we're taking the derivative of the function y with respect to x, and we would get what? 2x. Okay, so let's say that we use the derivative operator again. We take the derivative again. So if we take the derivative of the left side, this is just like anything else that we would do with equations. When we took the derivative here, the derivative of y with respect to x is dy dx. The derivative of x squared with respect to x is 2x. So if we take the derivative again, what we're doing is we're taking the derivative with respect to x of dy dx, and that's going to equal what? What's the derivative of 2x with respect to x? 2. And we could actually do it again, and again, and again. And with most functions, we can do it really as many times as we want. We could do it infinitely many times. We're going to start to see patterns in different types of functions. This one has a very simple pattern. What's the next derivative going to be?
0.
And then what's the next one going to be? 0. So all the other ones, all the higher ones than this are going to be 0, right? Let's look at this real quick, though. I want to look at this notation. On top, what we have is, and again, we're kind of treating these like numbers, like we would other variables, but not quite. But we have the derivative or the differential of dy, and the way we're going to write that is going to be this. And then on the bottom, what do we have? We have dx times dx, which would be, okay, it would actually be dx squared. Again, this is kind of treating it like they're variables or numbers. These differentials are a little bit tricky sometimes. But this right here is a notation that we're going to use for the second derivative. So the second derivative meaning the derivative of the first derivative. We could take a third derivative here, and what would be the notation for that? D cubed y over dx cubed. And what would that be for this example? 0. And we could take the nth derivative, and that would look like this. And as long as n is 3 or bigger, for this example, it's going to be what? 0. So when we're talking about higher order derivatives, we can take derivatives of derivatives. Since they're functions themselves, we can take derivatives of them. The nth derivative is what we call it. Let me write that down here. Nth derivative just means that we're taking the derivative n times. And for any polynomial, if n gets big enough, you're always going to get to 0. If we have things like sine, the derivative of sine is cosine, the derivative of cosine is negative sine. So what you're going to end up with there when you're taking more and more derivatives is it's just going to flip back and forth between sine and cosine with some sign changes in the way, along the way. So here are some notation things. The derivative of y with respect to x is written dy dx, or we could write it y prime. The derivative of that we write this way, which we just talked about, or you could write it y double prime. And so the nth derivative would be written this way, and we could write that kind of using an exponent, but not really. And I want you to notice here, the nth derivative of y is not equal to y to the nth power. Okay, so this means that we're taking the derivative of y n times. This means we're multiplying y by itself n times. So these mean two different things. These parentheses here denote that it's the nth derivative. If we're using the prime notation, if we get up to like the fourth derivative, we might use like y, we might use like y triple prime. So we might use that for the third derivative. For the fourth derivative and up, we could just do this, and that would be the fourth derivative, so that you don't have to keep writing primes. If you're going to do like the 100th derivative, which may seem silly, but when we're doing Taylor series later on, the 100th derivative could be useful. That would be a lot of primes, right? And then you'd have to count how many of them to know which derivative you're on, so this notation becomes useful there.